Okay, so part two, and I promise next we will move on to Black-Scholes and implied volatility, but before that I wanted to do one quick thing here. This quadratic equation, x squared plus 9, has no real roots, obviously, because this goes to 0 when, x squared is minus 9 or x is plus or minus 3i. So no real roots. Again, this is the derivative. It's the same as before. I just copied it into a duplicate function just because. And I ran our implied volatility, our root finding code here, and it doesn't succeed, obviously, because there are no roots to find. This is just a visualization of it. Obviously, it never crosses 0, and this function fails to find a root. I just wanted to put this in because this is one of the issues that people were having in the implied volatility code. I did a whole separate video on this, but they were searching for the way they had structured their prices. There was no solution to the equation, so that was the issue there. So I just wanted to put something in here, and now for real we will move on to Black-Scholes and implied volatility. Okay, so we've seen this 1,000 times by now. This is the basic Black-Scholes model. Price of a call, price of a put. It depends. This phi, remember, is the cumulative distribution function, the normal cumulative distribution function, and the d values that are arguments of that function are given here. So if we have a call option, say the price of that call option from our option chain is C0, we can write an equation like this. So our theoretical option price is a function of sigma, the implied volatility, minus that call price is equal to 0. So in other words, this is a root finding problem, as we've discussed before, and so let's actually just plug in some numbers and see what we get. So I'm just going to cut and paste our functions for the Black-Scholes call price and put price in. The only difference between this and the codes that I have shown previously is that I put the calculation of the d values directly into the function rather than in its own function. So, okay, let's go down here and let's write a separate function that'll play nicely with our Newton's method that we wrote up above, which we'll call it an objective function. So I've written two functions here. One is called objective function, and this is what we're going to actually pass into that Newton's method. And it takes two arguments. One is sigma here, which is our implied volatility, and the second is args, which is just going to be a list of variables, and that's going to be kind of deconstructed here. So the first element is the stock price, the second the strike price, risk-free rate, so on. Price is the price of the option, and then this function returns the Black-Scholes price minus that option call price. And since we need the derivative with respect to implied volatility, well, that's just vega. That's the definition of vega, and so I have a function here that calculates that. And likewise, it takes sigma and args, and it kind of pulls out everything from the args list and then returns the vega value. So let's just run this to see if there are no obvious typos. Okay, so far so good. And just to make sure this works, let us go back to our original test code for the implied volatility that I published probably about a year ago at this point. And we'll just steal our numbers from here. So stock price, strike price, time to expiration, risk-free rate, and the actual call price. So we will copy that, we will come back to our notebook, we will paste that in, and we will put it into an args list. So args is going to be equal to SKR, was it T, R, and C0. Let me just make sure that's the order that I have them kind of coming out in the function. SKRT, SKRT. Okay. And what was the initial guess of sigma here in this code? Where is it? We use 50%, so we will also use 50% in our Newton's method code back in the notebook. So, back to the notebook. Let us do something like, let's do it as R and count, and that is equal to Newton's method. Where is Newton's method? There you are. Objective function. Oops. Method. Objective function. Our derivative is calculate vega. Our initial guess is R is equal to 0.50 and args is equal to args. Let's see if that actually runs. Okay. I didn't realize until after I had finished the entire video that the audio went out on this part. So let me just say, rather than redoing everything and fixing the typos here, that this test code worked and prints out the same implied volatility that we got in our original code from last year. So having done that, now let's go on and look at some instances where this method will fail. So I added a little header here. It says test case just to make sure, this was just to make sure our code works. Let's go back to our equations. Now, the reason I spent all that time going over very simple cases was to show that the algorithm itself could fail in certain circumstances, and that should be obvious by this point. But now that we have a kind of a complicated expression here, we can have other potential issues. For example, let us say that we're very short, we're 0 DTE, we're at expiration. Well, this D term goes to, 1 over 0 basically will go up to infinity. That's going to cause a problem. Another potential issue is that sigma here is a width of a probability distribution. So it's a positive number. However, mathematically, there's no reason you can't put a negative number into this equation, and that's going to cause other problems. So let's come down here and let's actually plot. We'll use these, where are they? We'll use these values here, and we will plot the Black-Scholes call price as a function of sigma, and we will take sigma from like -1 to 1, so minus 100% to 100%. So let's come down here and do that. So sigma is equal to np.linspace -1 to 1. We'll do 100 points, and let us do plt.plot sigma. We will go call price of sigma actually the call price didn't take the args command, args variable, did it? It took s, k, r, and t. And now I want to plot it, and I'll use a blue line just to be consistent with what we did before. Close parenthesis. I have an extra semicolon for some reason. So there we go. Obviously, mathematically, that equation can take on negative values, which is going to be problematic. And also, there's this discontinuity at sigma equals 0 that's caused basically by the singularity in that equation. So this can cause a potential issue. Another potential issue is the fact that if this slope here, if vega is small, say you have a low cost option, low implied volatility, vega is small, the slope of this line is never going to, well, it might actually cross 0, but what happens then? So you come down here, it could potentially bounce back up to the right side, but you're not guaranteed that that's going to happen. So let's just run this code with some test scenarios, which should cause a problem. Okay, so case number 1, and I've cleaned up this plot a little bit, put in grid line, sigma, call price. Okay, so let's start with the simplest case, which I discussed in that original Debug Me video from a few months ago, where we have an in-the-money option and the price of the call is less than the intrinsic value of the option. So what I have here is the same as above, basically. The stock price is $100, the strike price is $90, so it's $10 in the money. Days to expiration, risk-free rate are the same, and the call price is the same. So this call should have some time value left in it, and it should have $10 worth of intrinsic value. So this should be more than $10, and it's, the number I have here is 2. So I define my args here, and now let's actually calculate the implied volatility here. And I guess you can know what the already know what the answer is going to be. Paste, run. Whole bunch of warnings and stuff, and not a number. Let's see how many iterations it actually ran for. 5. So let's see if we can debug exactly what's going wrong here. So I just want to plot to see what this function looks like. I'm just going to steal all of this code here, paste it in down here. And I'm going to change this call price to call price minus C0, because that's the function we're actually trying to find the root of. Okay, there's our function. And essentially this has no root. This solid line here is just because the points, it's just connecting the dots. So if I were to actually change that to, where is it plotted? Instead of a solid line, make it a dot. You can see what's happening here. It just reaches this price here and then jumps to a negative number, and then it keeps decreasing. But let's see if we can narrow it down even more and figure out where that not a number is coming from. So let's change this back to a blue line. Blue line. And we will come up here and we will do a debug equals true. Okay, so here we are. We see we get a very high value of the function, so that means a very high option price, and then it switches to negative, switches back to positive, and then all of a sudden we get an even bigger number for the option price and a slope of 0, which is causing the rest of our problems. There are two reasons we can get a slope of 0. I mean, obviously this function has no root, as we've said half a dozen times right now. But look here, where the function value or the implied volatility is small and the function value itself is small, you kind of have a zero slope. But you also could have, if I were to take this plot, where's my plot command here? If I were to extend this out to something like implied volatility of 1,000, you notice that you essentially get the same thing. Eventually you get a plateau in the value of this function and 0 slope, and that's what's happening here. So let's set this back to a normal value. Let's just set it to 1. And let's come back up here, and since we know the issue is the lack of a root, let's just bump up the call price to say $12.30. So there's $10 of intrinsic and $2 of extrinsic, which would give you a finite volatility. So you can see here the function has a root, and it looks like that root is about here, about 50%. And where is our value here? Here it is about 54%, and it only takes 3 iterations. So that's a possible issue you have to look out for, as we've said in the previous video. You know, make sure you have a root. So I'm going to set this back to our original value that gives an error, just so that it's there, and I will add some notes up here. So quickly here, I've added 2 other scenarios that can fail. In this case, it is the case where there's a short time to expiration and the option is far from the money. So let's just run this cell. I've already put in numbers here. So the stock price is 100, the strike price is 125, and there's half a day left to expiration, and therefore the option is really cheap. So let's just run that cell, and we get not a number. Again, not terribly surprising. Let's see if we can figure out why that's the case though. So let's come down here again and plot this out. We'll go sigma is equal to np.lin space. Let's go I don't know, let's go minus 0.5 up to 1, and we'll do 100 points. We will come down here and we will do a plt.plot sigma. We do not need the parentheses, comma, call price. That's going to be sigma S, K, R, and T minus C0, and we will do our obligatory blue line and the last parenthesis. So here's our function. You can kind of see what the problem is already. So let's get rid of this negative part because it's not really necessary. So let's come up here. Where? Here it is. So essentially our slope is 0, just like we saw with the cubic equation in part 1. So this is what's causing our problem here, where calculating the tangent line, the slope here is 0, and it's never finding an intercept because 1 essentially doesn't exist. And that's kind of what you see up here. Where is it? F prime slope of 0. And that, of course, leads to all sorts of problems. So that's the issue there. So, next case. The root is close to the discontinuity. So you remember we were plotting these functions out here, whereas you have this discontinuity at sigma equals 0. So if you were to have a very low volatility underlying and you had picked a value that was initial guess that was too far away, that can also cause some problems. So let's run that here. So again, this is a very low volatility position. The option itself is only 1 penny, risk-free rate. We're 30 days from expiration. The stock price is 100, and the strike price is only 50 cents above it. So based on these prices, you'd assume the stock is not going to move at all. So let's just run this, and I've already done the plotting here. What seems to be happening here is we are bouncing between positive and negative values of the objective function, and we're getting bigger and bigger values, and eventually we get a 0 slope, which causes problems. This plot isn't particularly informative, so let us, since we're getting big values of this objective function, it corresponds to large volatility. So let's just bump up our volatility in the plot to 100. So now you can see what's happening. It is essentially getting stuck on this area here, which is essentially 0 slope, and again we're back to that particular issue. This will converge if we were to put our initial guess, instead of r equal to 10, let's just do our default r is equal to 50%. So here we go, this does converge. Although we are getting a, looks like a divide by 0 error somewhere in there. It doesn't show up in the diagnostics. Okay, this is going way too long. Between this video and the previous part, we're probably pushing an hour, at least 50 minutes. So I'm going to stop here, and what I'm going to do is there are a couple little small topics I want to do as companion videos. There are things we've talked about a bit before, and 1 or 2 of them are just, to be blunt, they're pretty obvious, but just for the sake of completeness, I want to do something on them. So my plan for this root finding implied volatility thing is I want to do another algorithm on how to find the roots of a function, and I'm not going to use implied volatility in Black-Scholes just because I'm kind of sick of it. But after we do that, we will return to implied volatility and try to look at the vectorized code. A number of years ago, I purchased a bunch of option data on an underlying called UVXY. It's a volatility product, and I have tons of option pricing information on that. So we'll use that as our default because those were real world prices, and I've already kind of poked at it a bit, and they give a lot of, most of the time, 80% of the time it gives correct answers, but then 20% we get infinities, not a numbers, and so on. So that'll be an interesting test case. So cool. Until then, see ya.